Dr. Martin, are you saying anything? Because if you are, I can't hear you.
Very good. I forgot to unmute as usual. Thank you. So I was just mentioning that we're going to be talking today about the energy levels of the hydrogen atom. And so they're labeled by, these are the energies, and N is the principal quantum number. Okay, and so that's 1, 2, 3. It's a positive integer. Okay, and the minus sign here is telling you that these are bound states. Okay, and the E squared over 2A0 factor is 1 Rydberg. That's the energy needed to ionize a hydrogen atom from the ground state. Okay, and so that means from n equals 1 state to n equals infinity state. Okay, and the degeneracy of this, which we usually use G for degeneracy, is equal to 2 times 2 times n squared, where the first 2 is because of the electron spin, and the second 2 is because of the proton spin. And the n squared is due to angular momenta, different angular momenta. So in this, we have not included various small effects, and I'm just going to list them today. And these will be things that we will compute in Physics 661. So there are small effects, and I'm going to put here suppression factor. Okay, and so the first set of small effects is called fine structure. And the fine structure includes one thing we already talked about, which was relativistic kinematics. But it also includes the coupling between the electron spin and the orbital angular momentum. So that's called spin-orbit coupling. And then there's something else called the Darwin term. And all of these effects are suppressed by an amount which is the fine structure constant squared, which is 1 over 137 squared. So it's much less than a 1% effect, which is why we can get away with not talking about it sometimes. Okay, then there's something called the Lamb shift. And the Lamb shift turns out to be proportional to alpha cubed. So that's very small, but it just so happens it's multiplied by a very large number. And so it's actually not as small as you might naively think. And then there's something called hyperfine, which, as you might imagine from the name, is something much less than fine. And this is due to including the proton spin interactions. And so it's also proportional to alpha squared, which is a small number, but it's also multiplied by another small number, which is the mass of the electron divided by the mass of the proton. Okay, so these are the very small corrections to this formula right here for the energy. Okay, and then we were also talking about transitions between energy levels. Okay, and so the picture here is, let's say we have a state n, and we have a different state that's lower in energy, n prime, and then we transition from the higher state to the lower state, and we give off a photon in doing so. And then the wavelength of the photon we justified last time. You can write this as 9.11 times 10 to the minus 8 meters times n prime squared over 1 minus n prime squared over n squared. So there are different ways you can write that factor, but the way I've written it there is because what we want to do is we want to fix the final state.
Recording in progress.
Okay, and so we're fixing n prime. And for each fixed n prime, then you have a series of spectral lines for different n's. In other words, different starting states. And this is all for atomic hydrogen. Okay, so for different n. And these are given names. Last time we talked about the Lyman series. The Lyman series you start with, or you're going to end up with n prime equals 1. And so if n prime is 1, that means this is a pretty big gap. And so all of these are in the ultraviolet. And the first one is called the Lyman alpha line. The Lyman alpha line is when you start with n equals 2. The Lyman beta line is when you start with n equals 3 and go to n prime equals 1. And the higher up you go, the more the energy increases. So the largest possible energy that you can get in the photon is called the Lyman limit. That's when n goes to infinity. And these states, these lines here are very closely spaced because the initial states all have pretty close to the same energy. Okay, so that's the Lyman series. And then probably the most interesting series is the Balmer series, which is you end up with n prime equals 2. And the reason I say the Balmer series is maybe the more interesting one is that 4 of these lines are in the visible. So you can actually see them with the human eye. And they include n equals 3. Notice n is always larger than n prime. So n equals 3 gives you a red line. And you can see this red line in supernova remnants and in star forming regions that have lots of hydrogen in them. Okay, the other lines are also occurring, but the red one really stands out. And then n equals 4 to n prime equals 2 would give you a green line. N equals 5 gives you a blue line. N equals 6 gives you a violet line. And then everything from there on, from n equals 7 up to n equals infinity, or as n approaches infinity, those lines are also all in the ultraviolet. So you can't see them with the eye. Okay, and then there's the series with final state n prime equals 3. This is called the Paschen series. Okay, and so n has to be larger than 3, so n equals 4, n equals 5, up to the limit, which is n goes to infinity. And these are all in the infrared, sorry. And then the other named series are n prime equals 4, which is bracket. N prime equals 5, which is called fund. and n prime equals 6, which is called Humphreys. These are harder and harder to see. And they go on. I think they don't have names after that. Okay, so that's the experimental evidence that sort of confirms what we know about the hydrogen atom. And then you can look at all of these lines and include the fine structure, the hyperfine, the Lamb shift effects, and really get very detailed information that confirms the calculations. Okay, any questions on that before we move on to a different topic? All right, so the next topic we're going to enter into is going to be spin, which we've talked about a little bit, but we haven't really got into much detail. And so spin is intrinsic angular momentum. And so if you're talking about a single particle, there's a total angular momentum, which is traditionally called J, which is given by the sum of an orbital part plus the spin part. So J is total, L is orbital, meaning it just has to do with the actual motion of the particle. And spin, the important thing about orbital and spin is that they just completely commute with each other as operators. Okay, so there's no funny commutation relations that go between the orbital and the spin. You can just move those operators right past each other. So for an electron, S squared is h bar squared times s plus 1. Notice I'm writing a little s here because it's a number, not an operator. And s is just equal to 1/2. So it's fixed. There's nothing you can do to change the spin quantum number for an electron. And S sub z is h bar times a magnetic quantum number for it. If s is 1/2, that tells us the only allowed values for m sub s are plus or minus 1/2. Okay, so those s equals 1/2 can't change, but for the orbital part, those can change. So L squared is h bar squared little l times little l plus 1. L sub z is h bar times m sub l, right? And both of these can change, meaning I can have a state with any value of L I want, as long as it's an integer, and then I can find another state with a different value of L, and my states can change between one or the other. Okay, but for spin, it's fixed. You only get one value. So now, if we're going to talk about the state for an electron, we can write it in the following way. State for electron. I'm going to write here a ket for a capital psi, representing the state of the electron. And I can split it into two parts. There's a part that describes if m sub s is plus 1/2, which is often written as up arrow, plus a part that describes if m sub s is minus 1/2, right? So the up arrow and the down arrow are exactly the same thing as the m sub s spin label. I'm writing up arrow and down arrow, but I could just as easily write plus 1/2 or minus 1/2. And then for each one of those, the other part of this is the rest of the state information, which could be, for example, the position state, the position space wave functions. That information is represented by the psi up and psi down. So you can write it as a sum like that, but another way you can do it is you can represent it as a two-component vector of kets. Okay, so that would be a ket, and then the bra for that state would look like this. All right, so if you do it that way, these things are called spinors, just because they represent the spin information. And notice I did a sneaky thing, which is I changed the up arrow, down arrow notation just for variety into plus and minus. And I think, so there's different ways you can write these things. I think for the rest of today, I'm going to use the plus minus notation, but I could write up arrow, down arrow, or I could write plus h bar over 2 and minus h bar over 2, as long as we know that we're talking about spin up and spin down. Okay, so if we're acting on a two-component vector here in this representation, we can use matrices. And so the matrix representation for spin is we take the spin operator and represent it by h bar over 2 times the Pauli matrices, as we've talked about before. So the Pauli matrices are an x component, which is 0, 1, 1, 0, a y component, which is 0, minus I, I0, and a z component, which is 1, 0, 0, minus 1. Those are the Pauli matrices. And then we can have an inner product of spinors, which can be represented in two different ways that are just exactly equivalent. So one way is, let's say I have psi1 and psi2. Okay, I can write it in the sum version of things. Psi1 plus plus, that means spin up, plus psi1 minus, minus, and then acting on psi2 plus plus, plus psi2 minus, minus. Okay, that's one way of writing the inner product of those two states. Or I can write it in the two vector notation like this. Psi1 plus, psi1 minus. Now they are the components of a two-dimensional vector. And the same thing for the kets of psi2. And either way, so either way, this is equal to psi1 plus psi2 plus psi1 minus psi2 minus. In other words, the inner product just splits up into a part for spin up and a different part for spin down. And the things that you take the inner product of in that representation are the kets for up and down. So that's how you can take inner products. Then if you can take inner products, you can talk about the normalization. And so let's say we want the state to have norm 1. Okay, then the norm 1 should be the inner product of a state with itself. This time I don't need a 1 or 2 label because I'm only talking about one state. So this is psi plus, plus psi minus, psi minus. Okay, another thing we can do is we can talk about wave functions for these spinors. And so there are two component wave functions for electrons. And the way I do that is if I want a wave function, I take the inner product with a position eigenstate ket, sorry, position eigenstate bra, r theta phi, with my state psi. Okay, but the state psi has two components, one for spin up and one for spin down. So the wave function has two components. It looks like this. Okay, there's for up and here's for down. Okay, and that's just two wave functions, one in the up component and one in the down component. So if I write down a two-component wave function like that, that's the representation for the whole state. Okay. Okay, so if I'm writing wave functions like that, I've implicitly chosen a complete set of commuting observables for my representation. So all of this is in the R s squared s sub z representation, right? So the R represents the position, and then the rest of it represents the spin. And so this is the complete set of commuting observables that we have chosen. They all commute with each other. Okay, and then that representation, the number one for a normalized state, is given by integrating over all space times the sum of the individual wave functions squared. So in words, what we're doing here is we're saying we're calculating the probability, the total probability to be 1. And we're saying if you integrate over all places where the particle could be with spin up and add those all up to all the places the particle could be with spin down, we should get the total probability to be 1. It has to be somewhere, and its spin has to be either up or down. Okay, and in this representation, I'll just write in this rep, things like the z component of the orbital angular momentum are the usual things, except they're two component things because they have to act on two component objects, and they just act on the diagonal. Right, so if I do L sub z, it's the usual representation of L sub z in terms of derivatives, but it's just on the diagonal and zeros off the diagonal. Okay, so I'll just write et cetera here. That goes for any orbital angular momentum operator like L squared, et cetera. But now there's a different representation we could use by choosing a different complete set of commuting observables. So we could use instead L squared, L sub z, S squared, and S sub z as part of our complete set of commuting observables. Okay, so as part of the complete set of commuting observables. Why do I say part of? Because usually there's more to the complete set of commuting observables to fully specify the state. And so this will also include the Hamiltonian. That's the most usual thing, as long as it actually commutes with everything. So if the Hamiltonian commutes with orbital angular momentum, which it often does, and it commutes with spin, so if those commutators are all 0, then I can add it to the complete set of commuting observables. So if that's if I'm using that as my complete set of commuting observables, as usual, there's an orthonormal basis associated with it, with eigenstates of it. And so to specify a state in that orthonormal basis, I just have to tell you its eigenvalues for each thing in the complete set of commuting observables, which I can write as L and M sub L for these two. And then S, which is usually fixed, for example, to 1/2, and M sub S, that's for these. Okay, and then whatever is not being included, like the Hamiltonian, I can add another label for that, and I'll just call it K today because it may or may not be the energy. Okay, so K is other labels, which will often, but not always, be the energy. Or some quantum number like N in the hydrogen atom case that is associated with the energy.
When would K not be the energy? What else could it be?
So it might be some other weird operator that we're not going to usually treat too many cases like this, but it could be some other operator other than the Hamiltonian that commutes with L and commutes with S.
Okay. Thank you.
Yeah, I don't really have a good example because there aren't very many where it's actually a solvable problem. Okay. All right. So the thing is, so for example, let's say I was going to calculate L sub Z acting on such a state. Because we've chosen it to be an eigenstate of all these operators, I can just immediately write down that this is H bar times M sub L times L M sub L S, basically the same thing again. Okay, and if I were to write down L squared, same stuff, equals H bar squared, L times L plus 1, same state. Okay, and so in this case, in this representation, we often work directly with the Ketz and Bras. Okay, so there's an interesting fact that's going on here, which is that we're finding a way of representing states based on the angular momenta, but there's more than one way to do that. We've just chosen one way to represent the state in terms of angular momenta, and the fact that there's more than one way is what's sometimes known as addition of angular momenta. So let's go into that. So this is a general, very common problem in quantum mechanics. And so I'm going to start by doing it very generically, not even committing to the fact that it's orbital and spin. It couldn't even be two spins, or even two orbital angular momenta for two particles, or even more things than that. So let's just recall that there's such a thing as a generic angular momentum, where we're not going to commit to what it is exactly. Okay, and so I'm going to call it J, and it's just any three operators that are associated with X, Y, and Z that satisfy the following property. If I take the commutator of any two of them, JJ and JK, that's supposed to be I H bar times a sum over L of the antisymmetric tensor symbol JKL times J sub L, right? So J, K, and L here are any of X, Y, and Z, or I can just call them 1, 2, and 3. Okay, so there are generic angular momenta. They're just operators that satisfy this property. And now suppose we have two of them, which unfortunately I'm also going to label with subscripts because there's kind of no other way to do it. So suppose we have J1 as a vector and J2 as a vector. So for each of 1 and 2, there can be X, Y, and Z. And let's say they commute with each other. Individually, their components don't commute because they satisfy this. But the J1s all commute with the J2s. So now one complete set of commuting observables that we could choose is J1 squared, J1Z, just like we did for spin or orbital, together with J2 squared and J2Z. Okay, they sort of just ignore each other anyway, so I can just choose a complete set of commuting observables for each one separately and then put them together. And there might be other independent things like the energy. So I'll just say other things like the Hamiltonian. Okay, and so the eigenstates or the eigenkets of these operators I can write like this. There's J1, M1, tensor product J2, M2, which is really just a fancy way of saying that we've got some state that is a common eigenstate of those four operators. Right, and so you see that what we've just done is really exactly what we did up here with these states. Okay, and so more generally, the name we give to this strategy is we call this the product basis. It's an orthonormal basis, so we'll call it the product orthobasis. Okay, but another thing we could do is we could define the total angular momentum, J equals J1 plus J2. That's the total angular momentum operator. Okay, and then another complete set of commuting observables that we could choose is J1 squared, J2 squared, and J squared, and J sub Z. So we're not going to include J1Z and J2Z in this complete set of commuting observables. Notice they each have four operators associated with angular momentum, but they're just not the same four operators. So in this second case, the eigenstates are going to be labeled like this: J1, J2, J, and M. Okay, and this is a different basis. This is called the total angular momentum basis. Just because it has different labels than the previous basis. And so it's a very common problem that we'll have something in one basis and we want to change to the other basis. So the problem is find the coefficients that relate one basis to the other. So for example, find the coefficients for the state J1, J2, Jm as a linear combination. We know this can be done because they're both bases of J1, M1, J2, M2. Okay, so before we do that, let me just make one aside. So this is a big parenthetical comment, is you could say, could we have a different, a third complete set of commuting observables? Like, let's say, J1 squared, J2 squared, J1Z, J2Z, J squared, and J sub Z. Okay, so that would be our complete set of commuting observables. And so the naive answer might be no, because one thing we notice is that this complete set of commuting observables had four operators. This one had four operators. And now we're trying to have a complete set of commuting observables with six operators. And maybe the counting doesn't look like it's going to work. So that actually, it turns out it's true. This is not a complete set of commuting observables, but that's not really a very good argument, just counting operators. And so we should find some pair of these that don't actually commute. And so if you look at, for example, the commutator of j squared with j1z plus j2z, okay, that's actually just j sub z. And so that's 0. And so that one actually works. But here's what doesn't work, is if you take the commutator of j squared with just j1z. Okay, notice these are both in my alleged complete set of commuting observables. So all of these have to commute with every other one. And so if you write this out, this is j1 squared plus 2j1 dot j2 plus j2 squared, right? I've just expanded out j squared. And so there's this dot product here. That commutator with j1z. And the question is, does that vanish? And the answer is no. So one way you see that is j1 squared does commute with j1z. j2 squared certainly computes with j1z because j2 just ignores j1. But what doesn't commute is this j1 dot j2. So let me, actually I should put harpoons over them. So the point is, this j1 vector has within it j1x, for example, and that does not commute with j1z. So we could work out what the commutator was, but the important thing is just that it's not 0. Okay, and also that right away is enough to kill that as a possibility for a complete set of commuting observables. But just for the record, you could also compute j squared with j2z, and that's also not 0. And so the answer to the parenthetical question is no. So in some sense, it's too bad. If we could have a complete set of commuting observables with all 6 operators, then we would just use that and be happy and not have to worry about this problem of converting one to the other. But as things are in reality, they don't commute. They're not a complete set of commuting observables. And so we need to actually solve a problem. Okay, so before we start solving the problem, and we're not going to finish solving the problem today, let me mention there are 2 classic examples. And when we do start solving the problem, we're going to do these 2 classic examples. One is when you have 2 spins of distinct particles. So in this situation, I'm just actually going to be ignoring the positions of the particles and their orbital angular momentum completely. I've just got one particle here, and classically, well, sort of not semi-classically, its spin can point in any direction. Here's another particle, maybe it's in a crystal lattice and it's at a fixed distance, and its spin can point in some other direction. And so this is S1, and this is S2. So in our generic case, we're saying our J1 is really the spin of particle 1, and our J2 is the spin of particle 2. Okay, and so we want the total spin basis. And we do that by defining the total spin as the sum of the operators for the individual spins. Okay, and then from that, we construct the operators S squared, which is S dot S, and S sub Z. And those commute with each other. So they are a perfectly good elements of a complete set of commuting observables. So what we'll want to do is we'll want to write the eigenstates of the basis, the basis with S1 squared, S2 squared, S1z, S2z in terms of this basis with S1 squared, S2 squared, S squared, and S sub z. We want to be able to translate between those two bases. So notice in this example, S1 squared and S2 squared are just completely fixed anyway. They never change. The magnitudes of spins never change. And so there's really nothing to do when we worry about these two operators. They're just completely fixed. They might as well be numbers. Okay, but then there's this example, and this example is the one we actually started talking about, is for a single particle. Okay, you can have J1 be the orbital angular momentum and J2 be the spin. Okay, and so we will want to treat that case. Now, one thing you can do is if you can add two angular momenta and consider their basis, you can add those two angular momenta to another one. And so you can build up an eigenstate of many angular momenta. So by iteration, for example, you could consider a carbon atom. We're not going to do this semester. We'll do it next semester in 661, but a carbon atom has 6 electrons. Okay, and so the total spin is the sum of 6 individual spins. Just writing them all out. So there are 6 individual spins. And so one thing you can do is first add these two together, then take the result and add to that one, then take the result of that and add to that one, and add them all up. And you can do the same thing with orbital angular momentum. There's 6 of those because there are 6 different electrons. And then when you've got the total of all of those, you can add those together and get the grand total of the total angular momentum J. Okay, so that's sort of where we're going with this. That would be a particularly complicated problem with 12 different angular momenta associated with the state. But in principle, if we can add 2 angular momenta together, then we can do anything. Okay, so typically, we fix J1 and J2. That is the total angular, or sorry, the angular momenta of the 2 that we're adding together. And so they will appear in both orthobases, the total and the product, just as if they were ordinary numbers. And so the 2 orthobases that we're talking about are J1, J2, M1, M2. We might as well just drop the J1 and J2 and just write it as M1 and M2. Okay, then when you do that, it's understood that the J1 and J2 are fixed. And then there could be some ambiguity. You might have to ask, oh, wait, what J1 and J2 are we talking about? But there's some fixed answer to that question, right? So this is the product orthobasis. Product because it's the tensor product of the 2 individuals angular momenta, right? And the other one is J1, J2, Jm. And so again, we can just drop the J1 and J2 because they're fixed and just refer to these states as labeled by J and M. Okay, and this is the total. angular momentum orthobases. Or I might just say the total basis to be short. Okay, and so again, the general problem is that any given Jm state is a linear combination of the product states. So linear combination of M1, M2. And so we want to find those coefficients. Okay, and then there's the inverse problem. So if we have a state M1, M2 in the product basis, we can write it as a linear combination of the total angular momentum states. So it's a linear combination of states of the form Jm. And again, we would want to find the what those coefficients are. So it's going to turn out if you solve one of these problems, the other problem is almost immediately solved. We'll find that out next time. But another thing that we have to address is the fact that this notation can be confusing because in both cases, we're specifying the eigenstate by two numbers, in this case, M1 and M2, and in this case, J and M. And so if I just write down a ket with two numbers in it, you might not know which one I'm talking about. So the notation that I've adopted, and by the way, this is not standard. Lots of different books use lots of different solutions to this question. But my solution to this for notation is if there's a chance of confusion, then in the product basis, I'm going to separate them by a colon. So separate numbers in product basis by a colon. Some books just say, tough, figure it out, which it is. So in one case, we might do 2 spin 1/2 particles. And so we might have a state that's 1/2 colon 1/2. That would mean M sub 1 is 1/2 and M sub 2 equals 1/2. But if we're doing something complicated, we don't want to rewrite that every single time. And that's why we just put a colon there to tell us that we're in the product basis. So that's in the product basis. Okay, so I think that's about it for today. Next time we will start doing examples. And so next time, the examples we will do include 2 spin 1/2. So we'll figure out what the coefficients are between the product and the total angular momentum basis. That was sort of classical example number 1. And then we will do an application. We'll actually be able to figure out the hyperfine splitting of the hydrogen atom from this information. Okay, and so that will be on Monday. After that, we have holiday until the following Monday. So you owe me homework on this Monday, and there is, I believe, already on the website. If it's not there already, I'll make sure it is by the end of today. The last homework set of the semester, which is going to be due on the last day of class. Okay, any questions? All right, if not, then I will see you all on Monday.
Thank you.
Have a good weekend.